Let me now move over to one more notion of compactness. Yet again, we will work on general metric spaces. So let XD be a metric space to define the notion of compactness. We will have to first define what is meant by an open cover. So let script U, maybe I should write, we will be more careful, script U be a collection of open sets in capital X. We say that a subset K contained in X is compact. Oh, sorry. We say that, okay, I'll be careful, compactness comes later. We say that U is an open cover of a subset K if K is contained in the union of all the open sets in this collection. K is contained in the union of all the sets U, where U belongs to the script U. If this is getting satisfied, we say that script U is an open cover. Once we have the notion of what is meant by an open cover, very succinctly, if we have to describe compactness, it says that K is compact if every open cover of K has a finite subcover. Let me write that down. We say that subset K of the metric space X is compact if for every open cover U of K there exists finitely many elements, U1, U2 up to UN in script U, such that K is contained in the union of K from 1 to N of UK. So that means you start with any arbitrary cover U, it doesn't matter what that cover is, you will always be able to get hold of a sub collection which is finite and so that K is contained in the union. Let me give some very simple examples. One of the first example would be that all finite subsets of a metric space that will necessarily be a compact set. A finite subset of a metric space is compact. Empty set is compact. Another notion would be that you take a sequence of points xn converging to x. Let xn be a sequence of points converging to x or maybe x naught. Then the set A, which is the set of all xn, where n is in n. If you have not put 0 in n, let me just add it. This is compact. This is something which you should sit down and check in capital X. Okay, some properties of compact sets. In a metric space, a compact set is always closed. So let me just write it down as a proposition. In a metric space, a compact set is closed. Let's give a quick proof of this statement. We will prove that its complement, the complement of our given compact set is open. Okay, so let K contained in X be compact and X0 be in X minus K, the complement of K. Define define B subscript n to be all those points in capital X such that the distance, so d is the distance on X, the distance of X to X naught is less than 1 by n, less than or equal to 1 by n. So these are closed balls of radius 1 by n around X naught. And we will define U. Let U this be the collection of all X un, let me call it un, where un is equal to X minus Bn. So notice that Bn is closed because they are closed balls, therefore X minus Bn is open and therefore un is open. So U is a collection of open sets. And let's see what is there in the union, or rather let's see what is not there in the union. Then X minus the union of un. This is by De Morgan's law, this is the intersection of X minus un, right? So the n is from 1 to infinity, and X minus un is precisely Bn because un is defined as X minus Bn, right? So this is equal to the intersection of Bn. But what was Bn to begin with? Bn were, all the Bn's were closed balls of radius 1 by n. And you should check that if you look at the intersection, this is just going to be the point X naught. So the only point which is not in the union of un is X naught. But X naught does not belong to K, right? That is how we started off. Does not belong to K, and that implies that K is contained in the union of un, where n is going from 1 to infinity. Because X naught is the only point which is not in the union of un, and X naught anywhere does not belong to K. So K is a subset of this. This tells us that U is an open cover. The script U is an open cover of K. And that tells us that there is a finite subcover. Hence, there is an n that exists n in n such that K is contained in U1 union up to UN. We don't need beyond n. That is what this says. So let's pick m to be greater than n. That would mean that 1 by m is less than 1 by n, right? I'll allow you to sit down and check again. Check that the ball of radius 1 by m, this is contained in Bm, right? The closed ball, this is certainly contained in this. This intersected with the, this is easy. So check that this intersected with union of un. Oh, I shouldn't have used n everywhere. Let me call this n0. So there is this n0 and this is n going from 1 to n0. This is empty. But K is contained in this, which tells us that Bx0 1 by m is contained in X minus K. And therefore, you take any point in the complement of K, that has to be necessarily an interior point, and hence X minus K is open. Hence X minus K is open, and that's an alternate way of saying that K is closed. Therefore, we are always having a compact set as being a closed set in a metric space. So that's something which you should always keep in mind. So from now, because of this, okay, I'll also give one more exercise here. This is a good exercise for you to sit and work with open covers. It's not difficult, it's not straightforward either, but it's not difficult. The exercise is to show that if you take any closed subset of a compact, if you take a closed subset of a compact set, it should also be a compact set. A closed subset of a compact set is closed. So because compact sets are closed, we don't need to mention whether it is closed in the compact set or whether it is closed in the ambient metric space. When we say it is closed, we mean that it will mean that it is closed in both. Okay, so you should sit down and solve this exercise, and once we have solved this, the remark I am making right now is that it now doesn't matter whether we prove results on compact subsets of a metric space or on a compact metric space itself. So from now on, we will just assume that to talk about results on compact subsets, we will assume that the metric space itself is compact. Should necessarily have a limit point. So let X be a metric space. We say that X is limit point compact if every infinite subset of X has a limit point. If this condition is satisfied by every subset of infinite cardinality, then we say that X is limit point compact. The proposition. Let's start with a metric space which is compact. Let X be a compact metric space. Compact metric space is always limit point compact. Then X is limit point compact. We have to prove that if we take a infinite subset of X, then it should necessarily have a limit point. Now let's try proving that in here. Let A be an infinite subset of X. We'll prove by contradiction. We'll prove the theorem by proposition by contradiction. Suppose A does not have a limit point. If that is the case, the first observation is that if it does not have any limit point, then by default, vacuously, it contains all its limit points, and hence A is closed. A is closed in X because it contains all its limit points, which are none, by the way. And because A is closed, this implies that X minus A, the complement of A, is open. Okay, that's one observation. And the fact that A does not have a limit point means that given X in capital A, we can get hold of a neighborhood, that X is a neighborhood Ux of capital A, such that Ux intersects with A in just one point. Ux intersects with A in just one point X. If we are not able to get hold of any such neighborhood, that means that X is a limit point of A, right? So the fact that X is not a limit, the fact that A does not contain any limit point means that X is not a limit point of A, and therefore that X is one such neighborhood Ux. Let's now define a collection of open sets. This collection of open sets to be all the Ux where X is in capital A union the set X minus A, and it will be immediate to check that then U is an open cover of X. So we have now an open cover of X, which is a compact metric space. Remember that we started off with X being compact, and because it's an open cover of X of a compact metric space, there X is a finite subcover. There X is finitely many elements in U, such that X is contained in the union, and because X is the metric space, it will be equal to the union. And since X is compact, let me write that down. X is compact. There exists x1 to xn in capital A such that X is contained in, and the containment here is basically equality because X is the ambient metric space to begin with. This is equal to ux1 union ux2 union up to uxn and maybe x minus a as well. If x minus a is not needed, it's just redundant and we can throw it out, but nevertheless we can just say that there X is finitely many xi's which satisfy this. Then if you notice, A intersected with uxi is equal to just the point xi tells us that there are only finitely many xi's, isn't it? Because X is the union here, A and A does not intersect with the complement of A. This implies that A is a finite set because there are only finitely many sets whose union is giving us capital X. A is hence now a finite set, which is a contradiction, right? We started off with A, which is an infinite set. So our assumption has to be false. Hence, there exists a limit point of A, and that's precisely what we wanted. If you start off with a compact metric space, every infinite subset of that metric space will necessarily have a limit point, and therefore X is limit point compact. We'll define one more notion of compactness, which is actually equivalent in the setting of a metric space, and this is of sequentially compact. So we say that a metric space is sequentially compact if every sequence in the metric space has a convergent subsequence. Let me write that down and then we will describe what it says. Every sequence has a convergent subsequence. If we start off with a sequence xn in this particular metric space, then you can get hold of n1 less than n2 less than n3 and so on, such that xnk converges to some point x0 in capital X. So this is called a metric space which satisfies this condition is called sequentially compact. And the next proposition tells us that limit point compactness implies sequential compactness. So let me write that down. Let X be a metric space if X is limit point compact, then X is sequentially compact. So what do we have to do to prove this? We have to prove that every sequence will have a convergent subsequence. So let's start off with a sequence xn. Let xn be a sequence in capital X. We will collect all the elements which feature in the sequence in a set. Let's call that A. And A be this collection of all the elements xn where n belongs to natural numbers. So now there are two cases, either A is a finite set or A is an infinite set. If A is finite, then the situation is quite straightforward. If A is finite, that means that there is some element in this sequence which is getting repeated infinitely many times. There exists nk, k in n such that xnk is equal to some x0. in capital X. And if you take this particular subsequence nk such that nk is less than nk plus 1. So we get hold of such a subsequence, then limit k going to infinity of x and k is equal to x naught, and we have a convergent subsequence. So the case when a is finite is quite straightforward. We will have to work a little more when a is infinite, and that is when where the limit point compactness will start coming into the picture. Suppose a is finite, suppose a is infinite, then by limit point compactness, a has a limit point. Then a has a limit point, and let's say the limit point is x naught. Let's now get hold of a subsequence of xn which converges to x naught. That is the claim. The claim is that there is now a subsequence of xn which converges to x naught. To do that, let n1 in natural numbers be such that xn1 belongs to b x naught comma 1. So you pick one element in A which is in the ball of radius 1 around x naught, and then we will construct the sequence inductively. Let n2 greater than n1 be such that xn2 belongs to b x naught comma 1 by 2. So the first question you should be asking is, why is there one such n2? Give you a reason orally, you should write that down explicitly. Suppose there does not exist an n2 greater than n1 such that xn2 belongs to bx0 half. This means that the distance of xk to x naught is greater than half for all k greater than n1, and let delta be the minimum of the distance of x naught to xn1, x1, distance of x naught to x2, distance of x naught to xn1, and half. You take the minimum of all this, call it delta. And my claim is that the ball of radius delta by 2 around x naught, for example, does not have any element in A, and this other than x naught. Maybe x naught was already an element in A to begin with, but this will now tell us that x naught is not a limit point, which is a contradiction. So there should necessarily be one such n2 greater than n1 which belongs to the ball of radius half around x naught, and construct x and k inductively. I.e., let nk be greater than nk minus 1 such that xnk belongs to be xnk, bx naught comma 1 by k, and this x and k converges to x naught, and therefore we have now a convergent subsequence. X and k is a convergent subsequence. Hence, we started off with an arbitrary sequence, and we have proved that it should necessarily have a convergent subsequence. Therefore, X is sequentially compact. What have we proved till now? We have proved that you start with a compact metric space. It should necessarily be limit point compact. You start off with a limit point compact metric space. It should necessarily be sequentially compact. The cycle of ideas will be complete if we show that any metric space which is sequentially compact is necessarily a compact metric space. So let's complete that set of ideas, but before that we need a tool or a theorem which is called the Lebesgue number lemma. Let me write that down. The Lebesgue number lemma tells that if you take any sequentially compact metric space, there is some epsilon such that for every x, if you look at bx, given an open cover, there exists an epsilon such that for every x, the ball of radius epsilon around x is going to be contained in some element in the open cover. I will write that down and we will prove that as well. This is called the Lebesgue number lemma. Let X be sequentially compact. It's a metric space which is sequentially compact. I'm talking about sequentially compact. That means that X is a metric space. That's why I didn't write X to be a metric space explicitly, but yeah, this is the setting. And U be an open cover of X itself. That means X is contained in the union of all elements in capital U, but because script U, but because script U contains open sets in capital X, the union will be contained in capital X, and therefore here the fact that U is an open cover of X manifests in the form of X being equal to the union of all elements in the script U. Alright, so let U be an open cover of X. The Lebesgue number lemma says that then there exists epsilon positive, or let's call it delta. Epsilons will keep coming, so let's call it delta positive, such that for X in capital X, there exists U in the script U such that Bx epsilon is contained in U. Oh, Bx delta is contained in U. So this delta doesn't depend on X. It depends on the open cover U, but it does not depend on X. So for any X in capital X, there will be some element in the open cover such that the ball of radius delta around X will be contained in U. So this is what the Lebesgue number lemma says. Let us give a proof of this. The proof is by contradiction. Suppose we do not have one such delta. So suppose there does not exist a delta positive as above. What does that mean? That means that given any n, if you look at any 1 by n, there is a corresponding x or x subscript n such that ball of radius 1 by n around xn is not contained in any element in capital U, in script U. Let me just write that. Then for every n in natural numbers, there exists some point xn in capital X such that Bxn comma 1 by n is not contained in any element of script U. That is precisely what it says, what it means when we say that there does not exist any such delta. Okay, but what do we know about our metric space? Our metric space is sequentially compact. Since X is sequentially compact, we have a convergent subsequence, right? There X is a subsequence xnk converging to some point x naught in capital X. Now x naught is in capital X implies that there exists some epsilon positive such that B x naught epsilon is contained in U for some U in the script U. Why is this the case? This is because script U is a cover. Because script U is a cover, capital X is equal to the union of elements in script U. And x naught is a point in capital X means that x naught belongs to the union of all elements in script U, and therefore it belongs to some element in script U. Let's call that element capital U. But U is an open set now, and x naught is an interior point. So there is some epsilon positive such that the x naught epsilon is contained in our open set U. Okay. Now we are almost done. Let's pick nk large enough so that the distance of, so that 1 by nk is less than epsilon by 2, and the distance of xnk to x naught is also less than epsilon by 2. I will leave it as an exercise for you to check using the triangle inequality this particular claim. The ball of radius x n k 1 by nk is hence contained in U. So let me just write as that proof by triangle inequality. It's a straightforward observation. And this claim, if it is established, is a contradiction. Is a contradiction to which assumption? Is a contradiction, since we had assumed that, how did we pick all these nks, or how did we pick all these n's? The xn's will not be contained in any element of script U. That is how we had picked our xn's, right? So this is contradicting the assumption. So contradiction to the assumption that bxn 1 by n is not contained in any element of script U. So that means that this particular assumption has to be wrong, right? Because if we are starting off with this assumption, we are ending up with some kind of a contradiction. And therefore, there exists a delta positive hence there exists delta positive satisfying the conditions in the proposition, in the lemma. Okay, so Lebesgue number lemma, even though it is being called a lemma, it just captures something substantial. It says that if you have a sequentially compact metric space and if you have some open cover of the metric space, then there is some delta or some small number such that you take any set of diameter less than that number, it will be contained in one of the elements in the collection. Okay, so this is going to be used to prove that every sequentially compact metric space is a compact metric space. Let's state it, prove it, and finish or complete the circle of ideas. So let X be sequentially compact then X is a compact metric space. Once we establish this theorem, what we have finally proved is that a compact metric space should necessarily be limit point compact, a limit point compact metric space should be necessarily sequentially compact, and a sequentially compact metric space should necessarily be a compact metric space. So these three notions are equivalent in a metric space. Let's give a proof of this theorem. The first observation in proving this theorem is that the following claim: given epsilon positive, there exists finitely many points x1 to xn such that x is equal to bx1 epsilon union bx2 epsilon up to bxn epsilon. So given any epsilon, we will be always able to get hold of finitely many such points. The proof is by contradiction, proof of claim. Suppose that it doesn't happen for some epsilon, as proved by contradiction. Suppose epsilon positive is such that what will be the negation? there does not exist finitely many points such that x is equal to b x1 epsilon union up to b xn epsilon. That does not exist. This is the negation, right? If there is one such epsilon, we will arrive at some kind of a contradiction. The contradiction is basically as follows. Pick x1 in capital X. Inductively, pick xn plus 1 not in the union of the epsilon balls around x1 to xn. Remember that there will always be one such element, because if there is no such element at some point, that means that there are finitely many balls whose union of those epsilon balls will be equal to x. So that will be a contradiction already, right? We have picked epsilon, so that doesn't happen. So there is always going to be one such xn plus 1. And consider the sequence xn. But what is our assumption? Our assumption is that capital X is sequentially compact. Let me write it in shorthand form. It will be sequentially compact, and hence there exists a subsequence which converges. But what do we know about convergent subsequences? We know that convergent subsequences are Cauchy, but can a subsequence here be Cauchy ever? It will not be. However, distance of xj xk is always going to be greater than epsilon, since we have picked the points in such a manner, and hence no subsequence can be Cauchy. Which means that we do not have a convergent subsequence, right? Or it's a contradiction to the fact that, to the claim that there is a convergent subsequence, which is a contradiction. Let me just leave it at that. And therefore our assumption has to be false. Hence, there exists epsilon positive such that there exists finitely many points x1 to xn such that x is equal to b x1 epsilon union up to b xn epsilon. This particular notion is sometimes also called as total boundedness, but let's not get caught up in jargons. This is a claim which we have established for metric spaces which are sequentially compact. Now let's finish the proof by proving that it is now necessarily going to be compact. To prove that it is compact, let U be an open cover of capital X. And by Lebesgue number lemma, we know that there is an epsilon because it's sequentially compact. By Lebesgue number lemma, there exists a delta positive such that bx delta is contained in U for some U in script U, and which depends on x, right? So let me be a little more precise, such that given epsilon positive, bx delta is contained in U for some U in script U. But given delta positive, there exists finitely many points by above claim. Such that bx1 delta union up to Bxn delta is equal to our metric space capital X. So let's do one thing. Let's call this ux for some ux in capital X is what that'll help us identify these open sets. Then ux1, this left hand side is contained in ux1 union up to uxn, which now this contains bx1 delta union up to bxn delta, but that's precisely equal to capital X, which means that there exists the finite subcover. I don't want to use that word here, so let me say that hence X is just directly, let me write it down, X is compact. So we started off with, this is because we started off with an arbitrary open cover. Where was it? Let U be some arbitrary open cover. We managed to get hold of finitely many elements in the open cover such that it is union is equal to the given compact set, given set X, and therefore X is compact. Yeah, so with this we complete a circle of ideas. So from now on, because our complex plane is metric space with respect to the metric we have defined, these notions coincide in our complex plane, and we will freely be using these notions interchangeably. Okay, let me stop here.